Good morning. My name is Reverend Sister Florence Awoni. I am here this morning to take us through how to find the derivative of a polynomial function. Derivative has to do with differentiation of a function. Differentiation is all about measuring change. We know very well that integration deals with total size or value of a function, such as areas and volumes. Differentiation, on the other hand, look at the relationship between a function and the variables. When there is alteration or a change in a particular variable, what is the impact on the other variable? Suppose we have two variables, cost and strength or profit and loss. When there is a loss in terms of the money made from a business, what will be the reaction or the lesson the owner of the business will learn from that? Integration calculates area under the curve, but differentiation look at the rate of change of one variable with respect to the other variable. Now, suppose I have a function such as g of s equals to 5 plus 12s minus s cubed. You input this into the input bar and enter. This is what I obtain. This graph is so high up when it comes to y-axis. It's very long. So for us to see the beauty of this graph, I need to change the scale. At the moment, 1 centimeter is equal to 1 unit on both x and y-axis. But since the length on the y-axis is so large, I could alter the scale on y-axis to maybe 1 to 10. That is, 1 centimeter will be equal to 10 units. To do this, I right-click anywhere on the grid and choose Object Properties. So with Object Properties, I move to this portion to change it to 10, 1:10. And here I am with a beautiful curve. Now, this curve, as you see it, has gradient, different gradients at different points. It is possible you've been told before that it is difficult calculating the gradient of a curve. Yes, it is difficult, but we can estimate it using the tangent to the curve at any point in time. A tangent is a line that touches on the curve at a point, but it does not cut through it. And looking at this curve, if I attach a tangent at this point, the gradient of that tangent at this point will be different from the gradient of the line at this other point. So that is why we say that the slope of a gradient or the gradient of a curve is flexible. It's not static. It keeps changing. Unlike if you are looking for the gradient of a line, a linear function. For a cubic function, the gradient will change from one point to the other. So I need to locate a point now on this curve. So I go to the point icon and place it anywhere I like on the curve. If I could place it here, I could place it here, but let me put it just here to see what happened. So that is a point there. And the coordinates have been given on my left hand side as 2.4, 20. Now, I need to attach a tangent to this curve at this very point because I want to know the gradient of this curve at this point. So, looking at the toolbar, the eighth icon has the fourth icon has what I'm looking for. The fourth icon, it has the tangent icon. So I click on the curve and I click at the point where I want the tangent to be, and automatically GeoGebra attach the tangent, and the equation of the tangent is given on my left hand side here. Now, the next thing is I need to know the slope of this tangent. The slope of this tangent is the same thing as the slope of this gradient at this point. If I change my location, the gradient will also change. So the eighth icon menu has the icon for slope. So I need the slope of this line. So I click on the line and the slope is negative 5.22. The reason being that the curve is descending, is coming down. When it is descending, when the curve is descending, the gradient will be negative. When it is ascending, that is increasing, the gradient will be positive. So if I move from this position, remember you have to go back to your move icon for you to be able to move the point. If I move this point A from this place to another place, like I am here now, you see the gradient has changed to 8.09. And the equation of the line, of course, will change because we're moving from one place to the other. So that is how we get the gradient of a curve. And it changes along the line as you go up and down. It keeps changing. Now, the next thing for me is to remember we want to find the derivative of this cubic function. I need a line that will be located anywhere on the grid. So I pick a line using a point icon and place it anywhere. So automatically GeoGebra will label it for you and it is labeled B. So this point, I need the connection between this point and A. The point has its own coordinate as 1, -10. But I need to change it and I make sure there's a connection. How do I establish this connection? I want the gradient, I want the S coordinate of B to be the same thing as S coordinate of A. Then the y coordinate of B, I want it to be M. That is establishing that relationship such that the S component and gradient of A will be the same thing as the S component of B, where M, the gradient, will now be the y coordinate. Remember, we are looking for the derivative, and derivative's rate of change is established by using slope. So I'm going to my left hand side, double click on the coordinate of B and change 1 to S component of A, then change the Y component of B to M. Then I enter. The relationship have been established. Now, so there's a relationship between A and B. Then I will right click on B because I want B to be traced. I want B to trace A. I will choose trace on. Then I move my point wherever I like. And as I'm moving the point A, B is traced along that. Move anywhere, you will have the trace of B on A. You see that what we are obtaining here now is a quadratic function that is facing down, quadratic function facing down. That is what we have seen. And that is the derivative function of this cubic function. How do we know that? To find out if truly my trace is the derivative of the cubic function, then I go into my input bar and type the derivative of G. The derivative of G, once I type G prime, that is derivative of G, GeoGebra understand what I am saying, that I should find the derivative of G. And if the shape I get lies directly on my trace, then it means my trace and derivative mean the same thing. So I enter. As you can see, this is the derivative. The color is telling us that G prime is the derivative and it has given us a different color which is brownish. And my trace, of course, is purple. So it's superimposed, it's directly on top of my trace. So that is telling us that this is the same. The derivative of this cubic function and my trace of the cubic function is the same. Now, let us look at the curve and study it carefully. We see that the derivative of G remain above the x-axis as long as the function g of s is increasing. As this function is increasing, going up, the derivative of g of s remain above the x-axis. But as the function starts decreasing, then the derivative goes down below the x-axis. So that is what we see there. So it is above when g of s is increasing. So it is positive. And it is negative or going down below x-axis when g of s is decreasing. And looking at it also, the derivative is equals to 0 at this point. The derivative, that is g prime of s, is equal to 0 at these 2 points, negative when s is -2 and +2. That is the point where the curve touches the x-axis. At that point, the derivative function is equals to 0. These 2 points help us to estimate the maximum and minimum value. The maximum and or minimum value, depending on whether it's a cubic function or quadratic function, I mean the original function. So with this, the s is equal to -2. If you trace it to the original curve, the cubic function, we will obtain our minimum value. So the minimum value will be traced to y-axis. This point where my hand is, if I place a point there using GeoGebra, it will give us the minimum point. And the minimum point will have the x and y coordinate. Then if I come here to where 2 is and trace it up, this is the maximum. The maximum means there's no other value that can be greater for this function. The turning point is right here. It can no longer rise beyond this point. So s is equals to 2 there, and if you trace it to y, you obtain the value of y for that point. So we are going to use this our curve to obtain our minimum value and maximum value. Now looking at the graph, we can see that the minimum value lies between -3 and -1. The minimum value of this cubic function lies between -3 and -1. That is where the curve changes. And the maximum value, this is the maximum point here. The maximum values lie between 1 and 4. It lies between 1 and 4. So we are going to use this information to obtain our minimum value and maximum value, or minimum point and maximum point. So we go to our input bar and type minimum, and there's some options will come out for us. It's just one single function that I have, so I'm going to choose the fourth options given, and that is for minimum. So I will type, in order for this to have a name, I'll type minimum equals to, because if I do not give it a name, GeoGebra will give its own name. And the function I'm dealing with is g of s. I'll type g. Now start s value. The start s value, as you can see from this graph, is -3. It's just within somewhere here. I know it's somewhere. This is the point, but you cannot be too sure estimating it with mere eye. So it's better to use GeoGebra to locate it. So I'll put from -3, that is the s start value, -3, and the s end value is -1, because it turns. This is the curve here. It turns. It came down and started rising. So the minimum point is somewhere there. So I'll put -1, and then I will enter. So it has given me the minimum point to be -2, -11. So wherever I have -2 here, on x-axis, I'll trace it to y-axis. You know, it's so easy locating -2, but To locate that